Any questions before we start? Any questions about anything that we talked about on Monday? The first homework assignment is posted on Blackboard, and it is due on Monday. In general, there's a homework assignment due every Monday. So what we start to talk about today is Chapter 1, which is on set theory, which is the basic language for talking about mathematics for the past 150 years or so. Let's see, I see there's something in the chat. Oh, nothing, okay. So the basic notion is you have a set, which is a collection of objects, and the objects are usually called elements in general. So you might have a set S that contains elements X, and the basic notation is an element X. This is a Greek letter epsilon in S. So if you're not familiar with this notation, now you are, because we use it constantly. So favorite examples of sets, we have the integers, which are always denoted by a bold-faced letter Z, which you normally write like this on a piece of paper. So we have the positive integers and the negative integers, and that's the set Z. We have the rational numbers. Or fractions, which we denote by the letter Q. So you can't enumerate them in a simple way, but 2/3, -7/5, 0, 18/901, 3, which is 3/1, and so forth. These are all rational numbers. And then we have the real numbers, R. So this is just all real numbers. So it includes not just the integers and the fractions, but square roots or numbers that are not, that are pi or E, and so forth. It's all the numbers that you think of geometrically as being on the number line. And finally, the complex numbers. C, which is everything of the form x plus yi, where x and y are in the set of real numbers. All right, so these are just 4 examples of sets, and these happen to be sets of numbers. But all sorts of things are sets. Suppose A is the set consisting of dog, cat, and house. So this is a set that contains 3 objects, the word dog, the word cat, the word house, and you could say cat is in the set A, right? It's perfectly reasonable. Right? And what does it mean for sets to be equal? Sets S and T are equal, which is denoted S equal T, if every element of S is an element of T and every element of T is an element of S. So one way to say that is that X is in the set S implies X is in the set T, and if X is in T, that implies X is in S. And this double-headed arrow always means implies. Right? Another way of saying this is S equals T if the following condition is satisfied, X is in S, and then I write this double-headed arrow, X in T, and this means if and only if. That means if X is in S, then X is in T, and if X is in T, then X is in S. So this is some notation that's basically today is just a lecture on notation about sets. So if you let S be the set of even integers and T be the set of odd integers, then, so if, then S is different from T because, for example, 2 is an even integer, so 2 is in S, but 2 is not an odd integer, so 2 is not in T. Any questions about this? Let's look at another example. Suppose we let S be the set of all positive real numbers. That means the set of all X in R, all real numbers X, these 2 dots you would read often as such as, all X in R such that X is greater than 0. Right? Notice positive means greater than 0. 0 is not positive. Right? So S is the set of all positive real numbers. And suppose we let T be the set of all numbers X squared, where X is a real number and X is not 0. Okay. So S is the set of positive reals, and T is the set of the squares of all non-zero reals. Okay. So we can say, okay, so I claim these are the same. It's the same set of numbers, just 2 different descriptions. So a claim needs a proof. So if, for example, T is in the is a set in an element of the set T, that what does that mean? That means that T is X squared for X different from 0. And the square of a non-zero number is positive. and positive numbers, T is an S. So this statement says if T is in capital T, then T is an S. On the other hand, if little s is an element of the set S, then S is greater than 0. And if we let X be the positive square root of S, because we know in the real numbers, every positive number has a square root, then X is some real number, not 0, right? Because the square root of a positive number can't be 0 because 0 squared is 0. So if S is positive and you let X be the square root of X, then X is different from 0, which means that X squared is in T, because T is the set of squares of all non-zero numbers. But X squared equals X, S. So S is in T because X squared equals S, right? X is the square root of S, so X squared equals S. So another way of saying what I just proved, the second statement is that if S is in S, then S is in T. So every element of T is an element of S. Every element of S is an element of T. Therefore, S equals T. So this is a proof. This is in algebra. We don't just solve numerical problems like, solving a quadratic equation. You have to learn how to do proofs, and this is a proof. Okay. All right, so now I'm going to give a list of definitions or a vocabulary for set theory. So we have sets S and T. S is a subset of T. So that's the word I'm defining. And this is denoted S, and then a symbol like this. Well, there are two notations. So the one I use is with a bar under it. The book doesn't leave out the bar, but this is more standard. So this is the notation. If every element of S is an element of T, in other words, if X in S implies X is in T. So for example, if S is the even integers, S is a subset of Z, which is all integers. And you can also note it follows from the definition of equality of sets. S equals T if and only if S is a subset of T, and T is a subset of S. So we can rewrite the notion of equality in terms of subsets. Okay. Now, note also, every set S is a subset of itself. This just says every element of S is an element of S, and that's the tautology. That's kind of obvious. And we define the empty set which is denoted by this symbol. Is the set with no elements. So if you want to picture a set as, you have a suitcase and everything you put in the suitcase is what's in the set. If you don't put anything in, if the suitcase is empty, then you have the empty set. And again, the empty set is a subset of every set S, right? How could it be otherwise? The only way this could not be a subset of S if there's some element of the empty set that's not in S. But there is no element in the empty set. So every set S automatically contains the empty set. So every set S has at least two subsets, the empty set and the set itself. Suppose we let S be the set of all real numbers X such that X squared is negative. Well, but if you take a real number, the square is either 0 or positive. So there's no element X that satisfies this condition. So this is just a funny way of describing the empty set, because there is no number X, real number X, whose square is negative, strictly less than 0. If T is a subset of S and T is not the empty set and T is not the whole set S, then we say T is a proper subset of S. And you can often think of a set as like, here's the set S. Everything inside this circle are the elements of S. And if sitting inside S, you have a subset T, T is a proper subset of S if T contains something, but it's not the whole set. So this is a kind of a picture of a subset. Right. Any questions so far? All right, now, suppose we have sets S and T. The union of S and T, which is denoted S with a symbol like this, T. So this is the next word we're defining, and this is the notation, is the set S union T. It's all elements X such that X is in S or X is in T. So if you have a picture that say, here's a set S and here's a set T, the elements that are in S or T or both is this. Right. So for example, if S is the numbers 1, 2, and 3, and T is the numbers 2, 4, and 6, then what's an S union T? 1, 2, 3, 4, and 6. Because each of these numbers is in one or the other of these two sets, and every number here is in at least one of these two sets. Okay, questions? Okay. The intersection of two sets so this is our new word, our next word in our vocabulary. And this is denoted as, and this upside down symbol is S intersect T is the set of all X such that X is in S and X is in T. So if you wanted to draw a picture, this is the set S and this is the set T. The elements that are in both S and T are these. So that's S intersect T. So for example, if S is 1, 2, 3, and T is 2, 4, 6, then S intersect T, the only element that's in both sets is 2. So the intersection of these two sets is the set that contains just one element. So kind of a picture of that would be, let's say we have 1, 2, 3 in S and 2, 4, 6 in T. And what's in the intersection? It's just the number 2. When you draw pictures of sets like this, these are often called Venn diagrams. So a Venn diagram is just a picture of a statement about sets. Now you can have the following situation. Suppose S is the set of even integers. So 0, plus or minus 2, plus or minus 4, and so on. And T is the set of odd integers, plus or minus 1, plus or minus 3, plus or minus 5, and so on. Now, an integer is even or odd. It's never both. So S intersect T, well, this is all integers that are even and odd. There are none of them. So this is the empty set. Right? And we say, this is one more word, sets S and T are called disjoint if the intersection is empty. So a Venn diagram of disjoint sets is, here is S, here is T, and they have nothing in common, right? This set, in this set, there's no element that belongs to both of them, so the intersection is empty. Any questions so far? Now, I just defined union and intersection for a pair of sets, but it's easy and natural to extend the definition to more than two sets. So if S1, S2 up to S sub n are sets, then the union of these n sets, S1 union S2 union S3 dot 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 union S sub n, this is the set of all x such that x is in S1 or x is in S2 and so on, or x is in S sub n. So the union of a collection of sets is all elements that are in at least one of them. And I can, a more concise notation for this is just to write big U. I goes from 1 up to n S sub I. That's just another notation for this union. And this is the set of all x such that x is in S sub I for some I between 1 and n. Right? And similarly, the intersection of two or more sets, which we can write like this, or as intersection I goes from 1 up to n S sub I. This is all x such that x is in Si for all I going from 1 up to n. So for example, if we have three sets, let's say this is S1, this is S2, this is S3, what are the elements that belong to all of those sets? It's these. So It's that. Right. S1, S2, S3. These are the elements that are common to all three sets. So that's the intersection of the three sets. So let's just look at an example, have some fun here. Suppose I let S1 be 1, 2, 7, 8, 11. And S2 be 1, 3, 7, 9, 11. And S4 be 6, 7, 8, 9, 10. Sorry, S3. So write this down and calculate the following. S1 union S2. S1 intersect S2. S1 union S3. S1 intersect S3. S2 union S3. S2 intersect S3. S1 union S2 union S3. S1 intersect S2 intersect S3. So take a piece of paper and write down what these sets are. So if I take S1 union S2, what are the elements that are in one or the other of those sets? I have 1, 2, 3, 7, 8, 9, and 11. So each of these sets has 5 elements, but the union just has 6.
You forgot to write the number 7.
Oh, thank you. 1, 2, 3. Yeah, I was wondering about that. Thank you. What about S1 intersect S2? What numbers belong to both sets? 1, 7, and 11. Suppose I take S1 and S3. What numbers are in the union of those two sets? I have 1, 2, 6, 7, 8, 9, 10, and 11. And what is in the intersection of these two sets? It looks like just 7 and 8. Okay, any questions? What about S2 and S3? The union contains the numbers 1, 3, 6 through 10, and 11. And the intersection only has one element. Sorry, the intersection has 2 elements, 7 and 9. And if I take these 3 sets together, what's in the union? I have 1, 2, 3, There's no 4 or 5. And then 6, 7, 8, 9, 10, 11. And what's in the intersection of these three sets? The only number that's common to all of them is 7. Okay. Okay. Oh, and I should point out that sets with the operations of union and intersection do have properties similar to things like certain properties that are analogous to properties of addition and, let's say, just addition of integers. So for unions, we have unions of sets. We have an associative law, which says that if you take A union B union C, that's the same as A union B union C. Right? So what does this mean? You have your given sets A, B, and C. If you take the A union of A and B, and then you take the union of that set with C, you get exactly the same thing as if you took the union of A with the set B union C. And we also have a commutative law that A union B is B union A. Again, this is sort of clear because what is this set? This is everything that's in A or B. This is everything that's in B or A, but they're the same set. It's the same thing. We have another property, two properties, that A union A, if you take the union of a set with itself, this is just A. Because this says everything which is in A or A, which just means everything which is A in A. And A union the empty set is just A. Because this is everything which is in A or in the empty set, but nothing's in the empty set, so this is just A. And this is and we have another property which is interesting to think about, which says that A union B is equal to B if and only if A is a subset of B. See, why is this true? If something is an A union B, it's in either A or B. This means, but that's just B. So everything in A, if you take an element of A, it's in this. That means it's in B. So every element of A is in B. And conversely, if everything in A is in B, everything in A union B is in B. And for intersection of sets, we have similar properties. If we take, there's the associative law for intersection. A intersect B intersected with C is the same as A intersected with the intersection of B and C. Again, if something isn't here, it's in A intersect B and in C, but this means it's in A and B and C. So it's in A and B intersect C, yeah. And we have commutativity, A intersect B is B intersect A. The intersection of a set with itself is the set, and the intersection of a set with the empty set is the empty set, because this means everything in A in the empty set and nothing is in the empty set, so the set has to be empty. And A intersect B equals A means what? This means everything in A is in A intersect B, which means it's in B. So A is a subset of B. If and only if. If A is a subset of B, then the intersection of A and B is just A. A picture of these property D is the following. If we have a set B, which contains the set A, the intersection of A and B is just A, and the union of A and B is just B. So this is the Venn diagram that describes that situation. Okay. Well, this is just, again, learning words that we use in mathematics all the time. And for some of you, I'm sure this is familiar, but if this is not familiar, then you really need to spend a lot of time studying this section of chapter 1. Each chapter is divided into little bits that are numbered, and the terminology that the author uses these are articles of each chapter. So for example, if you happen to be looking at your book, this is chapter 1, articles so far 1 through 7. Okay. Let's go back to looking at our picture. Here we have a set S. Here we have a set T. The intersection is this. This is everything that's in S and T. But what can we say about this green area? This is everything that's in S. Is there a question? So what I shaded in green is everything in S that's not in T. So that's called the difference. And it's denoted S minus T or S slash T. Both notations are used. Is what? This is the set of all X such that X is in S and X. How do you say something is not in a set? You put a slash through this epsilon sign. X is not in T. So this green indicates all the elements of S that are not in T. That's S minus T. What is this region that I'm shading in blue? These are all the elements of T that are not in S. So T minus S, which is this blue region, is all X such that X is in T and X is not in S. And again, there are lots of very pretty properties of this symmetric difference. What about if I take the green and the blue together? So S minus T union T minus S what is that? That's all X such that either X is in S but not T, or X is in T but not S. So this is all X such that X is in S and X is not in T, or union, all X, so that X is in T and X is not in S. Of course, another way of saying that is, if I look at S and T, I take everything in the union, but I throw away the elements that are in both, minus S intersect T. And the notation for this is what is called the symmetric difference. Of S and T, and it's usually denoted with a star or an asterisk, S intersect T. So again, if I have two sets S and T, this is the intersection, and everything which is not in the intersection, but is in either S or T, is in what's called the symmetric difference. So the green and the blue together, that's the symmetric difference. So let's just look at one very simple example. Suppose S is 1, 2, 3, 6, 7, and 8, and T is 6, 7, and 8. Ten, 11, 12. So the union of S and T, let's see, let me do this a little bit differently. Let me write this as, so this is S. Let's say I'll make T 4, 5, 6, 7, 8, 9. So the union of S and T is all the numbers from 1 to 9. The intersection of S and T, 6, 7, and 8. Okay. Let's draw a picture. So this is S. T is 4, 5, 6, 7, 8, and 9. This is T. So this is the intersection, 6, 7, and 8. The difference, S minus T, everything in S not in T, is 1, 2, 3. The difference, T minus S, everything in T that's not in S, is 4, 5, and 9. And the symmetric difference, everything in the union that's not in the intersection, 1, 2, 3, 4, 5, and 9. Okay. Any questions so far? All right, well, still not done. Let's keep going. There are some more constructions about sets, or terminology if you like. So suppose there is let's say a big set or a universal set. Let me call it X. And we are considering only subsets A of X. So we have some big set X, and all the sets we're looking at are contained in X. So what is called the complement with an E, not an I, it's not, we're saying that nice. The complement of A is the set A star, which is everything that's not an A. That means everything in the universe which is not an A. So if this is A, A star is everything else.
Can you move the screen just a little bit downward, Professor?
Okay. And in this section on the terminology and notation of set theory in chapter 1, there's one last construction, which you know from calculus very well, which is called a Cartesian product. So the Cartesian product of sets S and T is the set, which we write S times T. And this is a set of ordered pairs. It's all pairs X comma Y, such that X is in S and Y is in T. So for example, in calculus, the XY plane, R2, or R times R, is the set of all ordered pairs X and Y, where X and Y are both in R, right? So this is R2. This is just a picture. Right? Or if we take, for example, S to be the unit interval, that's all X in R, where X is between 0 and 1. And suppose I take T to be the interval 0, 2, which is all Y in R, such that Y is between 0 and 2. Then the product S cross T, which is the set 0, 1 times the set 0, 2, that's all ordered pairs X and Y, where X is between 0 and 1, and Y is between 0 and 2. And if you draw a picture of it, it's this rectangle in the XY plane. And there are a couple of homework problems for Monday, which are exercises 9 alpha and 9 beta. So this is the notation the textbook uses. The articles are numbers. So 9 is the article, which is like a paragraph number. This is And when there are problems, they're given Greek letters. So 9 alpha is the first problem in section 9. 9 beta is the second section in problem in article 9, and so forth. This is homework. Okay. Any questions so far? All right. See, this is all a lot of stuff. This whole first chapter is really like preliminaries for the course. It's setting down the language that we use to talk about mathematics, and just have to learn the words. So the next section in chapter 1 is on mappings, or another name for that, functions.
Sorry, Professor, can I interrupt you for half a second? So I just want to make sure I'm doing the correct homework. So can you go back and explain again with the 9 alpha and the 9 beta, please? Sorry.
Okay, so do you have the textbook?
So not in front of me, it's coming, sorry.
Okay, so so the way this book is written, each chapter, let me see if I can show this. Here's chapter 1. This is just an introductory paragraph. And you see it starts, you see there's 1, 2, 3, and so forth. So each of these little sections are called by the author articles. This is in the first chapter, article 1, article 2, article 3, article 4, and so on. Here is article 9. And here you see 9 alpha and 9 beta. So these are the homework problems.
Fantastic, great, thank you.
That's the way the book is. And the articles they don't change the numbering, they don't restart the numbering in each chapter. So if you go to, the middle of the book, here we're up to article 112. This happens to be in chapter 3. But the way this book is written, whenever there's an exercise in an article, it has the article number and then a Greek letter, alpha, beta, gamma, and so on. So that's just the funny notation this author uses for exercises, homework problems. Okay, so we defined the Cartesian product. So suppose we have sets X and Y, and we want to think of the idea of a function or a mapping F from X to Y. And this is no different from what it is in calculus. It's just slightly more general because it applies to arbitrary sets. This is just a rule which gives to every element of X some unique element Y. And one way to define this, a definition of a function or a mapping is a mapping F is a subset of the Cartesian product of X and Y such that for every X in the set capital X, there is a unique element Y in the set capital Y such that the ordered pair XY is in F. F is a subset of the set of all ordered pairs. And we write either Y equals F of X, or sometimes simply Y equals Fx, or sometimes F sends X to Y. So But it's just like, you know, so if X and Y are equal to R, and F is the set of all pairs X comma X squared for X and X, then for any element F, F of X equals X squared. This set of ordered pairs is the function F of X equal X squared. Right. So this is just generalizing a little bit the notion or the definition of a function. Okay, let's see. And again, there are certain things which are sort of obvious. If you remember a little bit of calculus or pre-calculus even. Suppose we have functions or mappings f and g in x cross y. We say that f equals g. This means f of x equals g of x for all x in x. Right? It's exactly the definition you would use in calculus. And one particular mapping, which you know very well, is the identity function. So if we have a set X, the identity function in X cross X is the function defined by 1 of X equals X, sends X to itself for all X. So as a set of ordered pairs, this is a set of ordered pairs X comma X for X and X. I mean, in general, what is called a relation is simply a subset of the Cartesian product, and a mapping is a relation which has this additional property that there's exactly one ordered pair X comma Y for each X in the set X. Okay. And suppose we have a function f from X to Y, what is called the image of X of f. IM is image of f. It's the set of all y such that f of x equals y for some y, for some x in x. So this is just like saying, suppose we have the function from R to R given by f of x equals x squared. If we graph that function, we get a parabola. The image of f, well, what are the y's that you get? It's all the squares. The image of f is all x squared, which is the same as saying all non-negative numbers, right? Because the squares are the non-negative numbers. So just look at the graph, and the y values, I'll use a y maybe, all y which are greater than or equal to 0. And the following words are important. The function f from x to y is called onto if the image of x of f is all of y. So the function f of x equal x squared is not onto, because the image of f is a proper subset. This means subset but not equal to, is a proper subset of R. If f is not onto, then f is often called into. So the squaring function is into but not onto. If you take the function f of x equal x cubed, that's what the graph looks like. And for this function, the image of f is all of R. So f of x equals x cubed is onto. Okay. Well, a lot of words you have to learn to do mathematics. But we're not done yet. The best is yet to come. So let me just draw a picture of this. Suppose we have a set X and we have a set Y, and this function or mapping from X to Y, sitting in here, you have the image of F. All right? So X, every element X gets mapped to some element Fx contained in Y. That's the image. We can also try to go backwards. Suppose we have X and then we have Y, and this function F from X to Y. Suppose over here, we take a set B. So what is called the inverse image of B is what? It's the set. So this is denoted also as F inverse of B. This is all X in X, such that F of X gets mapped into B. So if I take an element X here and it gets mapped into B, then it's in the inverse image of B. If I were to take an element, a different element X, and it gets mapped to something over here, it's not in B, so this X is not in the inverse image of B. So the inverse image of B so this is F inverse of B. This is all the elements of X that F assigns a value in B. And what's very nice are functions that have the property of being called one-to-one. The function F is 1 to 1. So these are all words. Function F is 1 to 1 if n inverse of y contains at most one element for all y in y. So let me draw a picture of what that means. I have X and Y sets and a function between them. The easiest thing is to say what it means if a function is not one-to-one. If it's not one-to-one, you have elements X1 and X2 that are different, but they get mapped to the same element over in the set Y. Fx1 equals Fx2. So if I take this element in Y and I say, what element in X gets mapped to Y? There's not a unique element. There are at least two of them. There could be none, that's okay. But if there are two or more elements that get mapped to any single element of Y, this function is not one-to-one. One-to-one means every element of Y has a unique inverse. So f of x equal x squared is not one-to-one. Because, for example, f of 2 and f of minus 2 give the same value of 4. F of x equal x cubed is one-to-one. Because x cubed equals y cubed if and only if x equals y. So these definitions you must have seen in calculus, and they extend more generally to arbitrary functions. Any questions so far? I mean, there's a lot to learn, but that's just it. There's a lot to learn. Let's really go back for a second to looking at subsets. Suppose X is the set, I don't know, A and B, two elements. What are the subsets of X? Well, you always have the empty set and X, and you have two other sets, A and B, these sets with 1 element. So let's say that what is called the power set of a set X is the set, we write it as 2 to the power X, of all subsets of X. So for example, if X is equal to AB, then the power set of X contains all the subsets, the empty set X, A, and B. Right? And you'll notice there are 4 of them. The set X has 2 elements, and the power set has 4 elements. Let's take another example. Suppose X has 3 elements, A, B, and C. So what are the subsets of X? You have the empty set and the whole set. You have 3 one-element sets. And you also have 3 two-element sets. And you notice X has 3 elements. The power set has 8 elements, and 8 is 2 cubed. Okay. Oh, there's one more notion I need to define, which is extremely important. So suppose we have a mapping or a function X from X to Y. So recall F is onto if F inverse of Y is not empty for all Y in Y. Or equivalently, if for all Y in Y, there is at least one X in X such that f of X equals Y. And F is one-to-one if for all Y in Y, there is at most one X in X such that f of X equals Y. So if a function is onto for any Y, there's always at least one X in the set X that is mapped to Y under the function F. And if it's one-to-one, there's at most one such X. So F is one-to-one and onto, which is also called a one-to-one correspondence if F is both one-to-one and onto. So for example, f of x equal x cubed is a one-to-one correspondence. If you look at the graph of y equals x cubed, it's from R onto R. And for every y, there's exactly one x such that x cubed equals y. So y equal x cubed is a pretty example of a one-to-one correspondence. I defined the integers and I discussed the integers. The positive integers n, so n is the set of positive integers, which are also called the natural numbers. So this is the set of the positive integers, 1, 2, 3, 4, 5, 6, and so on forever. So this is a subset of the set of all integers. And n sub k is just the set of the first k integers. So here is a definition. A set S is finite. What does it mean for a set to be finite? If either the set is empty, so empty set is finite, or there is a one-to-one correspondence F from S to nk for some k positive integer. So if you have a set S, and if there's a one-to-one correspondence between the elements of the set and the first k integers, it's called a finite set. And we say that the number of elements of S which is also called the cardinality, is k. And we say a set S is called countable, or sometimes countably infinite, if there's a one-to-one correspondence F from the set to the set of all positive integers. All right, well, maybe that's enough for today because there's a lot of terminology. We're not really proving any theorems, but we are learning the language of mathematics. This is what we need to do. Okay, that's it. I will normally have 2 or 3 or more sort of office hours on Zoom when anyone can just log in and ask questions about anything in the homework or the lectures. Because everyone has complicated schedules, I try to have them at different times of the day, maybe morning or afternoon, evening, and on different days. So I definitely will have an office hour problem session, whatever you like to call it, on Friday morning. And then there'll be a regular schedule starting next week. Okay. But if you have a question, don't hesitate to send me an email. And I always get back to you fairly quickly. Of course, I check my email several times a day. Okay. Anything else? Is that it? Okay. That is all for today. Take care, everyone.
Have a good day, Professor.
Thank you. You too.
Bye, Professor. Have a nice day.